So in this assessment, you are going to have to work through some wave stuff and conceptually and mathematically. The first one says wave A has a longer wavelength than wave B. So what that looks like in my head is this is wave A, whereas wave B might look like this. So which wave has a higher energy? In this case, it would be wave B has the higher energy. What do I know about it? I know that shorter wavelengths, higher frequency, higher energy. So that's how I came to that conclusion. Next one says, after watching green light have enough energy to cause electrons to leave a metal in a photoelectric effect, Noah and Alejandro have a discussion about whether purple light could also have enough energy to leave the metal. Noah says it will because purple has a higher frequency than green light. Do you agree or disagree? So in this instance, I would agree with Noah. And I would say that light that has a higher frequency and in this case, I'm going to put purple, has more energy. Meaning that it will be able to eject an electron. Okay. In the next one, you're just reading this diagram and answering some questions about it. On your practice quiz, over here on the right-hand side, we wrote red, and over here on this side, we wrote violet. That's probably for later, but it's black and white on your paper, so we wanted to make sure that you had that in front of you. Now, what type of wave has what type of electromagnetic radiation has a wavelength of 5 times 10 to the minus 1 nanometers? So if I go up here and I look at wavelength, which is on the top of the diagram, I'm looking for anything that has something times 10 to the minus 1. And I see that something times 10 to the minus 1 is going to be right about there. So that tells me that this is going to be an X-ray. The next one talks about frequency. So we're talking about what that is a frequency of 1.2 times 10 to the 10 per seconds, and frequency is on the bottom. And so in this case, I'm going to be looking for anything that has something times 10 to the 10 on the bottom. And that appears to be right there. So that tells me that this is going to be a microwave. And then it says, identify one type of wavelength that is longer than ultraviolet light. So looking back at my wavelengths, up on top, ultraviolet light is right here. And as you go to the right, every single one of those different types of electromagnetic radiation is going to have longer wavelength than ultraviolet. So the most complete answer is it could be visible. It could be infrared. It could be microwave, or it could be radio wave. Any of those is correct. You only had to put one of them. And then lastly, you were asked to identify one type of electromagnetic radiation that had more energy than microwaves. So when we talk about energy, when looking at the spectrum, we have to remember that the ones with the shorter wavelengths have the most energy, and the ones with the longer wavelengths have the least energy. So we are looking for something that has more energy than microwaves. So that could be infrared. It could be visible. It could be ultraviolet. It could be X-ray. Or it could be gamma radiation. Any of those is correct. You only needed one. Any questions on the first page? Okay, so now we had to perform some calculations involving wavelength and frequency. The first calculation says what is the wavelength of a wave that has a frequency of 9.51 times 10 to the minus 1 per seconds. So the only formula that I see that has wavelength and frequency in it is the C is equal to wavelength times frequency, the one right over here. And so that's the formula that I'm going to use for the first one. So if I'm going to if I'm going to identify my variables, C is equal to wavelength. Oops, that's not right. Times frequency. And then I'm going to go ahead and fill in my variables. I know that the speed of light, or C, is always going to be 3.00 times 10 to the 8 meters per second. And I'm given that the frequency in this case is 9.51 times 10 to the 7 per seconds. So I'm going to plug those in. So I'm going to take the 3.00 times 10 to the 8 meters per second, solving for the wavelength, when I know the frequency to be 9.51 times 10 to the 7 per seconds. I'm going to use my calculator, and I'm going to solve by taking 3 times 10 to the 8 divided by 9.51 times 10 to the 7th. Help if I put in the calculator right. 3 times 10 to the 8 divided by 9.51 times 10 to the 7th. And I get a value here to be in the general area of 3.15, and the unit there is going to be meters for my wavelength. The next question asks me to convert meters to nanometers. So 3.15 meters to nanometers. And when I convert, I need to use this relationship here that says 1 meter is equal to 1 times 10 to the 9 nanometers. So I'm going to put my 1 meter on the bottom and my 1.0 times 10 to the 9 nanometers on the top. So I'm going to take 3.15 times 1 times 10 to the 9, and I get something like really big number. Yeah. What happened there? Did I do that right? 3.15. Oh, I didn't put that in the calculator. 3.15 times 1 times 10 to the 9th gives me something like this. So I get something like 315 with, let's see, 1, 2, 3, 4, 5, 6, 7 zeros after it. 1, 2, 3, 4, 5, 6, 7 zeros after it. And that's a correct answer, and I will accept that tomorrow, but that's going to be in nanometers. But what I'm really going to be looking for probably would be to convert that to scientific notation. So 3.15 times 10 to the 4, 7, 8, 9 nanometers would be the answer I'll probably really want tomorrow. But, there you go. Yes?
If you write it both ways, and if one's wrong, you still get credit for the other one's right?
I would prefer, the question is, can we write it both ways? And if one is wrong and the other one is right, can we get full credit? I'm going to say, got to pick away.
So, like, if I were to write it like this, you would have given me a 0.
I would have, well, is that 7 zeros after it?
Yeah.
Then that would be correct.
Oh.
All right. The next one asks you to identify the frequency of a wave when you know the wavelength is 4.10 times 10 to the negative 12 nanometers. So we're still going to use this formula, the speed of light formula, where C is equal to wavelength times frequency. And in this instance, again, 3.00 times 10 to the 8 meters per second. This time I know the frequency, or the wavelength, to be 4.10 times 10 to the negative 12 meters. That was really nice of us. You didn't have to convert. So I'm going to take the 3.00 times 10 to the 8 meters per second is equal to the 4.10 times 10 to the negative 12, and that's meters. times the frequency, which is what we're trying to solve for. So 3 times 10 to the 8 divided by 4.10 times 10 to the negative 12 gives me a frequency of 7.32 times 10 to the 19, and that's going to be per seconds for my frequency. Questions about these two, or these three? Okay. Next one says we have a photon that has an energy, so it has an energy of 3.027 times 10 to the times 10 to the minus 19 joules. And we're looking for the photon's frequency. So we're looking for the frequency. And it doesn't say anything about wavelength, so I probably don't need that formula. So I'm going to use the energy formula, which E is equal to Planck's constant times frequency. And in this problem, we know the energy is 3.027 times 10 to the negative 19 joules. And we also know that Planck's constant is 6.63 times 10 to the negative 34, and that's joule seconds. And we're solving for frequency. So I'm going to plug these in. So I'm going to take the 3.027 times 10 to the negative 19 joules, and that's going to equal Planck's constant's value of 6.63 times 10 to the negative 34 joule seconds, and times frequency. So I'm going to solve by dividing both sides by Planck's constant. So 3.027 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34. And here I'm going to get a frequency of 4.57 times 10 to the 14, and that's going to be per seconds. Questions about that?
How did you type in joule and or you just not type it?
You don't type in joule.
Okay.
Okay. Question was, how do you type in joule in your calculator? And you actually don't need to. All right. Next one is a little bit more complicated. It is asking you to solve for the wavelength of ultraviolet light when you know the energy to be 2.39 times 10 to the negative 18 joules. So I'm going to take some time to identify the variables that I have. C, because this one's the more complicated one. Then we have wavelength. Then we have frequency. And then we have energy. And then we have Planck's constant. And then we have frequency. So just like we did in the homework, we're going to identify what we know. We know that the speed of light constant is 3.00 times 10 to the 8 meters per second. We know that Planck's constant is 6.63 times 10 to the negative 34 joule seconds. And then we also know that the energy, because the problem tells us this, is 2.39 times 10 to the negative 18 joules. So given the information that I have, it looks like I'm going to need to use both formulas at some point. And given the fact that I have energy, Planck's constant, it looks like I can solve for frequency. So I'm going to start with the energy formula. So energy is equal to Planck's constant times frequency. So in this case, energy is going to be, 2.39 times 10 to the negative 18 joules is equal to Planck's constant, which is 6.63 times 10 to the negative 34 joule seconds times the frequency, which we're going to need to solve for. So 2.39 times 10 to the negative 18 divided by 6.63 times 10 to the negative 34. I get a value for my frequency to be something like 3.60 times 10 to the 15th, and that's going to be per seconds. And now that I have that, I now have the ability to solve for wavelength using the speed of light formula. So speed of light is equal to wavelength times frequency. Speed of light is 3.00 times 10 to the 8 meters per second. Wavelength is what we're solving for. And the frequency is the number from above, so that's going to be 3.60 times 10 to the 15th, and that's going to be per seconds. So 3 times 10 to the 8 divided by 3.60 times 10 to the 15th gives me a wavelength of 8.33 times 10 to the negative 8, and that's going to be meters, is my wavelength. And it doesn't ask me to change it to nanometers, so you're good there. Questions about this one? All right, the next page, or the last page, asks you to go ahead and identify some light stuff in terms of electrons. So when an electron moves from an excited state down to its ground state, has energy been released or absorbed? The most correct answer here is going to be energy has been released. Comparing the two models below, we have a photon of red light and we have a photon of blue light. And looking at the diagrams or the models, we have to figure out which one is which. So what I'm going to do is I'm going to scroll back up to this diagram up here, and I'm going to see that we're comparing red and blue basically. So we're going to be comparing red light to blue light. And what we know, or what we remember, is that red light has a longer wavelength, so it has lower energy. Blue light has a shorter wavelength, so it has higher energy. So that means that the other thing that we have, so the one that drops the lowest is going to be the blue light. So that, or the most. So this one will be blue light because it dropped from N6 to N4. And this one will be the red light because it dropped from N6 to N5. Okay, so the one that dropped the most is the one that has the more energy, and as a result of that, that's the one that's blue light. So how would I explain that? Well, I would explain my reasoning by saying that the electron that dropped the farthest released more energy blue light has a shorter wavelength, so it has more energy. And so then the next one, you were supposed to identify how many electrons would fit in each energy level. And this one came pretty much from the chart that you filled in class yesterday. So the first energy level can hold 2 electrons. The second energy level can hold 8 electrons. The third energy level can hold 18 electrons. And the fourth energy level can hold 32 electrons. And then lastly, which level would have its electrons furthest from the nucleus, the second or the fourth energy level? And the fourth energy level is furthest from the nucleus. So there you have it. That is the answer key to your practice quiz. Tomorrow's quiz will look very similar to this, so I highly suggest you take the time to go ahead and review tonight. Good luck.